Okay, can you all hear me once again?
Yes, sir.
Yes, sir.
Right. Okay, good. A good news, huh? You all are coming to the faculty by 2nd of September, isn't it?
Yes, sir.
Ah,
sir.
good. Everybody is happy, huh? Back to school, huh? Good. Okay, so this may be the last lecture on Zoom. So once you come here, we will have one-to-one lectures, right? We might do a summarization of what we have done for past 1.5 months. Once we come here, we will do it. All right. Okay. If you look back where we stopped last time, we started with the first conventional design. That is basically called as CRD in short in form, complete randomized design. So that is the very basic design. All right. So this is the very basic conventional design. Conventional means that is the lower level of design. We are going to talk about the advanced design later on. So this is the lower level of design. This is like a foundation for all the designs, right? Complete randomized design. This is actually expansion of pool t-test. In pool t-test, always we can compare two treatments, isn't it? We can compare two treatments. All the time we compare two treatments, right? So we compare, let's say, T1 versus T2, right? T1 versus T2. This is a pool t-test. Pool t-test, right? If you have only two treatments, let's say we have T1 and T2. We have only two treatment, then we will go for T1 versus T2. Suppose if you have more than two treatment, let's say we have a situation, three treatment, T1, T2, and T3, three treatments. So if you ask to do t-test, you have to do t-test how many times? T1 versus T2, T1 versus T3, and T2 versus T3. So how many times you will have to do it? 3 times. You have to do t-test 3 times, right? Later we will talk about when you do t-test 3 times, there are some other problems arises. Can you remember the error? How do you call this error? In your first course we talked about, how do you call this error? There's another name for this. This is alpha error. So how do we call this alpha error? Another name for the alpha error? Anyone? Anushan, what is the another name for this alpha? Type 1 error. Have you heard about this? Can you remember? Type 1 error. What is beta? What is beta then?
Type 2 error.
Type 2 error, right? Right. So you see, when you have more and more comparison, the type 1 error will increase. We will talk about that later. So because of that, it is not advised to do t-test on an individual basis. Therefore, the solution to come up with if you have more than 2 treatment, go for ANOVA, analysis of variance. We have introduced this ANOVA during our first course, another regression, somebody said last time. So we go for ANOVA, analysis of variance. So we can put these three treatments to the basic design. The first design that we are learning is complete randomized design. It's called as CRD, complete randomized design. Okay. Right, now we will continue with our design, which we have mentioned last time. So this is the extension of ANOVA, as we said, right? And also CRD design is the extension of this full t-test, as I mentioned. This design is ideal to conduct experiments, especially in a area where the experimental units are more or less homogeneous. Experimental units are more or less homogeneous. We talked about experimental unit in our first class. Experimental unit could be a small plot, or maybe a pot, or maybe a petri dish. Any kind of material can be considered as experimental units, right? So some examples for homogeneous is laboratories, plant houses, etc., etc. So experiment will use very few replicates. So we need only very few replicates, right? So let's say I have treatment 1, T1, T2, and T3. So replicate 1, we put it as R, replicate 2, replicate 3. Similarly, replicate 1 for treatment 2, replicate 2 for treatment 2, and replicate 3 for treatment 2. So likewise, for all treatment, we can put up the replicates. But generally, if the experimental units are more or less homogeneous, we can have a less number of replicates. That is the speciality. Treatments are assigned to experimental unit at random. So that is true for not only this design, in any design. RCBD, we will come to that a little later. So any design, treatments are assigned on a random basis to all the experimental units. Each treatment is replicated with the same time of same number of replicate. So it is called as balanced design. Last time I mentioned what is balanced design, right? Can you remember what is balanced design? If all the treatments are appearing in single block, it's called as balanced design. Right, so this is how randomly allocated. All the treatments are randomly allocated for different experimental unit. Look at this nicely. We said this is a balanced design because all the treatments are appearing 4 times. All the treatments are appearing 4 times, right? So this is not a balanced design. This is not a balanced design because the number of replicates for each treatment is differs. Look at this design. Again, number of replicates is more or less same, but only problem is they have been not randomized. So that is the problem with this kind of arrangement. There is no randomization, right? So again, the same problem, no randomization because the green color has been pushed to one corner. The red color one has been pushed to another corner, and the yellow color has been pushed to the third corner. So that randomization is not really took place. So this is the formula for a complete randomized design. This is not formula, this is called model, right? This is the model for complete randomized design. We have seen this also. Yij, right? We mentioned about the units or the digits. What is this I, and the I is indicating treatment effect, right? J is indicating the replicate. I is indicating treatment. So which is starting from 1 goes up to T. J is replicate, right? Starting from 1, 2, and goes up to R. Then we said about the error term. This is the error term. Error term is more specific for one particular unit of treatment and the replicate. Right? I think we did do last time the right. Did we talk about all this? Yes, we. So these are some of the notes that you can go through it. We did last time. We stopped, I think, somewhere there, as I remember, isn't it? So we will start up from today, from that point onwards. So basically, source of variance. These are the main component of the ANOVA, source of variance, degrees of freedom. DF means degrees of freedom. SS means sums of square, mean square, and F calculated value. So treatment, that is your first source, right? So degrees of freedom is T minus 1. The total degrees of freedom is we have T number of treatment, R number of replicates, so T into R minus 1. So that is total degrees of freedom, right? So how you get error degrees of freedom? Error degrees of freedom is always total minus treatment. Total minus treatment. Okay. So last time I showed you how you get this value, error degrees of freedom, T into R minus 1. Then we have sums of square. We will see how to calculate the sums of square. This sums of square for the treatment. SST mean write down sums of square of treatment. SSE means sums of square of error. Write down what is the abbreviation for SSE. Sums of square for treatment, sums of square for error. Then we have sums of square of total. So again, the error sums of square, which is coming actually from total sums of square, SS total minus sums of square of treatment, right? So this error sums of square error is coming like total sums of square minus the sums of square of treatment. Clear? Is it clear? Anyone having questions? You can write down on chat if you have any questions. Right. How we calculate the mean square? Mean square is calculated as mean square of treatment. MST mean square of treatment is sums of square of treatment divided by the respective degrees of freedom. So sums of square divided by degrees of freedom is given as mean square. Right? So we calculate the mean square for treatment as well as mean square for error. We don't calculate the mean square for total. Why? Because we want to compare the mean square of this treatment and the error only. Right? We want to compare only these two mean squares, not with the total mean square. so that we don't need to calculate the total mean square. Finally, we comes to the comparison of these two mean square, which is giving the FL. So mean square treatment divided by mean square error. Okay. Right. We talked about this. Now we are going to put up some equations and see. Right. Now what is this? The same ANOVA. Here the ANOVA is same thing. Now I have elaborated with some notations here. So we will look at what are those notations. All right. So before we talk about those notations, I will explain what are those notations. Right. Let's say I have three treatments: T1, T2, T3. For the time being, I am comparing only. So R1, R2, R3. What are these R1 and R2, R3? Anyone?
Replicates.
Replicate, right.
Replicates.
So the first digit, let's say we said Y, I, J. What is this I? I indicating what?
Treatment.
Treatment. What about J? It's indicating
Replicate.
replicate. Now tell me, if I write this T1 R1, how can I write in terms of Y?
One.
First first treatment? First
Y11.
Right. What about this?
Y21.
Y21.
Right, Y21. What about this?
Y31.
Right. You can complete the table now. Y,
1, 2.
1, 2, Y, write down, 1, 3. Similarly, Y, 2, 2, Y, 2, 3, Y, 3, 2, Y, 3. Clear? Right. Now, I just put the line here. Right? Is it clear? Now, if I write, for example, Y, I put it as summation. Summation means summing up. I'm going to add this plus this plus this. What is difference there? What is constants there among these I and J? What is the different? What is same? What is different? Anyone? Look at the digits I and J. Tell me by looking at this I and J.
Treatment same, replicative.
Treatment same.
Exactly.
Replication.
Replicative ones.
Yeah, we can say which treatment? If I add Y11, Y12, Y13, which treatment is that? Belongs to which treatment?
T1.
Yeah, it's same treatment, but which treatment?
T1.
T1, first treatment, right? So it is first treatment total, isn't it? This is the total of first treatment, Y11, right? So in other term, I will use another piece of paper. For example, Y11 plus Y12 plus Y13. We can write this as summation Y. Can somebody say, what is this? 1 dot. This is how we write it as. That means it is the first treatment total. Write down, first treatment total. first treatment total. So this is how. If I say y summation y2 dot, it is the second treatment total, and so on. All right. I'm going to change the page. Write down first treatment total. So this is summation y1 dot. Now, can you write all this? Tell me how I can write this y1 dot. What about summation? This one, summation y2 dot. This is summation y3 dot. Similarly, tell us how I can write this. I mean, actually, we don't want this information now. How I can write this, for example? Can somebody tell me? Summation y. Think in similar way.
Summation y dot 1.
Exactly. That is the first replicate total. Isn't it? First replicate total, irrespective of treatment. Similarly, this is summation y dot 2. Summation y dot 3. Actually, we don't want for this particular design, but this is how we write it down. Give me a second. Some unwanted things are popping up. All right. And now, this one. Right here, can somebody tell me if I add all these, y11 plus y12, y13, y21, 22, 23, 31, 32, 33. I add all elements. So how I can write y? Anyone? How many elements are there? These are elements, huh? You did matrix, right? So these are called as first element, second element, third element, and so on. How I can write? If I add all the values, y, anyone? Dot, dot, y dot, dot. So that means it is the total. So this is called as grand total. Grand, huh? This is called as grand total. Is it clear? Right. Now, anyone having questions? If you don't know how the notations are arranged, then we have a problem. Right? If the notations are arranged, cannot be identified by you all, then we will have a problem. Right. Now, okay. Now we have, you see, first component is treatment, T minus 1 degrees of freedom. Now you understand, right? We can put summation or we can put the y dot dot, doesn't matter. So this is a general summation, right? Coming for everything. Summation, look at this first component, right? That is actually summation. I will use not enough space, so I will use somewhere there, right? So this summation, what we are doing is summation, this formula, summation of y I dot square divided by r, where this I is from 1 to t. So this is the formula that I am using here. So that is equal right? Y1 dot square plus y, right, 2 dot square. What we have seen, y1 dot square. What is this? Anyone? We have
First
seen.
treatment is constant.
Yeah. What? How do you call this? It is the total of first treatment. It is the total of second treatment. So likewise, it goes up to yt dot, because we don't know. This is a general term. T dot square, squaring it up, right? Divided by respective replicates. So here, if you have same replicate, no problem, we can divide by the common term r. Sometimes there may be a possible different replicates, right? Different replicates are possible. For example, right? I don't have this one. I'm just erasing, right? So what about T1? How many replicates are there for T1? 2 replicates are there. For T2, 3 replicates are there. For T3, 3 replicates are there, right? So the replicates are not same. So the dividing R will be different. So in this case, we are dividing by 2. In this case, we are dividing by 3. In this case, we are dividing by 3. Okay? So that we'll have to remember always. Right. Now we will further discuss on our ANOVA table. Any questions? So this is the expansion of the treatment sums of scale, right? Minus, right, treatment sums of scale. This minus, can you remember we have seen something like this, grand total. So grand total square divided by the TR, treatment and replicate. TR, number of treatment, and multiplied by number of replicates. Clear? So this is the formula that we will use it. Right. The sums of square of error simply calculated as total sums of square minus sums of square due to treatment, SST. So this is SST. This is the total sums of square. So total sums of square is given as summation of double summation of Yij square, where I is from 1 to T, J is from 1 to R, minus again grand total square divided by TR. So this is called as correction factor. It is called as correction factor. This is called as correction factor. So grand total square divided by TR. Clear? Any questions? We'll do a sum later and see. Okay. Now the mean square is simply sums of square divided by their respective degrees of freedom. So this is the degrees of freedom for treatment. This is the degrees of freedom for error. So treatment sums of square divided by treatment degrees of freedom, which is giving the mean square of treatment. Mean square of error is given as sums of square of error divided by degrees of freedom of error. Then we have F calculated value, which is simply mean square of treatment divided by mean square of error. All right. So this is how we calculate the F value. The most important is this value. F, sometimes we call it as FC, calculated value. Can you remember in first course we talked about TC, T calculated value, TT table value. Similarly, we have F calculated value, FC, which is coming or calculated from this ratio, and also we have FT table value. So table value we can look at from the table, F table. Right? Right. Now, based on this F table, we'll have to make the decision as we did in other cases. To make the decision, we'll have to have some format. What are those formats? First thing is, what is our hypothesis? We said this is the first treatment effect, second treatment effect, and so on. This is the last treatment effect. These treatment effects are equal to 0. Right? So that is our null hypothesis. What is the alternative hypothesis? At least one of the alpha differs from 0. One of the alpha is differs from 0. At least one of the alpha is differs from 0. At least, right? So at least one of the alpha is differ from 0. So if it is so, then we accept our alternative hypothesis. Then we have test statistics that we have already seen. Your F calculated value, that is given by mean square of treatment divided by mean square of error. Mean square of treatment divided by mean square of error. All right? So decision making process. The decision making process is based on this, right? Decision making process is based on this. What is our calculated value? F calculated value greater than FT. For example, this is the same thing as we did. This is the F distribution. Suppose, let's say this is what region is that? If my alpha is that region, so this is sorry, F, yeah, F table value. Let's say F table value is somewhere there. So this region is called as rejecting region, right? That region is called as rejecting region. Now, if calculated value is greater than table value, so if calculated value is greater than table value, means calculated value will fall into this rejecting region. Then we reject our null hypothesis. Suppose if my calculated value is less than the table value, it will fall into non-rejecting region. So we can not reject our null hypothesis. Is it clear? All right. So this is the decision-making process. So it's true for any test. Not only this test, it is true for any test. Right. Now we will do a small sum. Right. Yeah. Before we do the small sum, we will talk about. We'll do a sum. Do we need to do a sum, or we will continue with our next topic? Later on we can do the sum. What do you prefer? Which one would you like to prefer? Which one will you like? Yeah, anyone? Okay. Then some members have said that we will do a sum. When we do the sum, you'll have to answer. That is the thing, right? I don't have a calculator. You'll have to calculate and let me know what are those values. Is it clear? Otherwise, I will catch those who said we will do a sum. There are few members, 4 or 5 members said that we will do a sum. Good, no problem. Right, now we'll go to, right, we'll do a sum, right? Let's say I have 3 treatments, T1, T2, T3. Let's assume they have same replicate, right? So R1, R2, R3. I have some value, right? Let's say weight gain. What do you mean by weight gain? Anyone who is doing animal science? Now you people have to answer. What is weight gain? Let's say these are 3 rations. For animals, we are giving 3 rations. This is ration 1, right? T1 means ration 1. T2 means second type of ration. T3 means third type of ration. Now tell me, what do you mean by weight gain? Anyone? Vishmika? Anyone from animal science? The students who are specializing from animal science. No animal science. I will ask from Dr. Vadani, who are the people doing animal science. Shall I? What is weight gain? Weight gain is given for a period, isn't it? Let's say I am giving these rations, different rations. After giving the ration, we can, let's say you have initially, as an example, that particular animal is 30 kilogram. After feeding with this ration, after 1 month, we measure the animal again, the same animal. Suppose, let's say that animal is now 35 kilogram. That animal is 35 kilogram in 1 month. In 1 month, don't forget, right? So what is the weight gain? What is the weight gain? 5 kilogram per month in that month, right? 5 kilogram per month. So when you do the experiment, you'll have to, how many experimental units are there? Can somebody tell me how many experimental units? You can answer through chat. How many experimental units are there in this particular example? 3 rations, 3 replicates. So how many experimental units? Let's say it is cow or piglings. Easy to get piglings. How many piglings? Yes, 9 experimental units. Let's take pig. Pig is easy to get because in one calving, how many piglings that you can obtain at once? How many piglings you can obtain at once? Let's say 9. So we can use all these 9s for this treatment because they are siblings. So we are treating these siblings with different ration, T1, T2, T3. So here the weight gain is, after treating with T1, let's say the weight gain These are very 2-month old piglings. So weight gain here is 2 kilogram, here 2.5 kilogram, 2.8 kilogram weight gain. All right, from treatment 1. Let's say treatment 2, 3.1, 3.3, some values, 3.6. This is 2.8, 2.5, 2.4. Right? This is also say 2.2. These are the values. Now tell me, what are the totals? Now you'll have to tell me all these values. This way total is not necessary. This way total is not necessary. Now, what is the first treatment total? Get all this.
7.3.
7.3. You see how many answers are coming. 7.3, 7.5. You can use the calculator.
7.5.
Good. Okay. So that is what I said. I am very poor in calculating. Assuming. All right. 7.5. What about this second treatment total?
10.
10. Third treatment?
7.7.
7.7. Right. Now, this calculation is enough for the time being. So we can calculate treatment sums of square. That is, for example, summation y I dot square, right, divided by r minus y dot square divided by tr. Don't forget this formula, right? So this is called as treatment sums of square. I'll put it as treatment sums of square. Right? So what are the treatment sums of square now? We can calculate treatment sums of square is equal 7.5 square root plus 10 square root plus 7.7 square root, whole thing divided by, what is r here? Is the r same for all treatment or different? Number of replicates. Yeah, is the r replicate same or different?
Different.
Why different? What about first one? What about first treatment? How many replicate?
3.
3. Second treatment?
3. Same.
Third treatment?
3.
3. Same. So if the number of replicates are same, no problem. We can divide by directly. So can somebody get the answer? I need only one answer. I don't want 60 of different answers. I need one answer.
71.84.
Anyone having a different answer?
No, sir, same.
Same. Good. Right. Keep that in mind. It may need to fill our table. Right. Somebody else send me chat. 8485. Okay, doesn't matter. Is it 71.84? Huh?
846.
Huh?
85.
85. Okay. Let's say keep this in mind. This is called as treatment sums of square. Right? I'm going to erase this now because we need all. I'm going to erase some of this. No space. Now, what is the correction factor? How to calculate the correction factor? I need this table. That's why I'm doing all these children's work. All right.
Grand total square by
Let's say treatment sum square is 71.85. So keep that in mind. What is the sorry? This is not treatment sum square. This is just this is not treatment sum square. Right? This is summation y I dot square divided by r. Right? That is not exactly treatment sum square, right? This is summation y I dot square divided by r. So this is the value. Now we want to calculate this one. I dot square divided by tr. What is that? So for that we'll have to calculate the grand total. What is the grand total? $25. What is the value of this total? 25 point.
2.
Now the way that you calculate is 25.2 whole thing square divided by what is t into r? What is t? What is the value for t?
3.
What is the value for t? Number of treatment 3.
3.
What is the value for r?
3. 3.
Yeah. So tr, what is the value? 9.
9.
So get the value. What is the value? Don't send me chat now because I tell the values verbally. Yeah. So I'll have to look at the chat time to time, wasting time.
70.56.
70 point.
56.
Okay. 56. Okay, fine. So what is the treatment sum square then? 71.85 minus 70.56. Is it clear? So that is equal somewhere around 1 point something. 1 point, tell me, 1 point z
1.28.
28. Right. So this is the treatment sum square. Keep this in mind. When we fill our table, we'll have to answer these values. I'm going to raise some of it. Right. Now, sum square for treatment we have calculated. Now, we want to calculate the sum square for total. So that is, can you remember the formula? Double sums comes yi j square minus the correction factor. If you look back, all right. If you look back, again it is not. Right. You see, this is the formula. This is the formula that we are going to apply. Okay. Right. Now we will go back to the calculations. So I said C, it is a correction factor, right? The correction factor is same. So once we have this is the correction factor. Once you have calculate the correction factor, you can keep it for other calculation as well. So this is actually something like this. First observation 2.2 square plus what is the second observation 2.5 square plus third observation 2.8 square plus fourth observation 3.1 square. So how many observations are there altogether?
9.
9. So you'll have to square all these. So I'm writing the last one plus 2.4 square, right? After that, minus this correction factor. This is 70 point something. Can somebody get me the answer? What is the total sums of square? What is the total sums of square? You'll have to do it correctly, huh? Because these are very minor differences, values.
$72.24.
Okay, somebody said 72.24
24.
minus 70.56. Is that correct? So this is the addition of all the squares, isn't it? So what is the final total sums of square value?
1.68.
1.68.
1.68. Right. So keep these two in mind, right? This is 1.68 and this. I'm going to go to the next table. Is it clear to everybody? Is it clear or do you need any clarification? If you need any clarification, I will have to ask who need the clarification and what sort of clarification are you all looking? Hmm? Right. Right. Now we are going to fill the table. Now we are going to fill the table. Very difficult to move this. Yeah. Right. Now I am going to fill the table. I'll put everything in very short form. All right. ANOVA table, right? I'll put it as a source of variance, SV. What is next? Degrees of freedom. Sums of square. Mean square. F value. Calculated value. Right. What are the source of variance? Treatment. How many treatments are, what is the degrees of freedom of treatment? How many treatments are there? T minus 1. So what is the number of treatments? How many treatments were there?
3. 3.
Treatment. 3. Look at the formula. T minus 1, right? Sorry, T minus 1. So T is 3 minus 1. 3 minus 1 is 2. So nicely fill this table. Huh? This is called as ANOVA table. So what about next one? Next one is total. What is the degrees of freedom of total? TR minus 1. So what is T? 3. R is 3. So 3 into 3 is 9 minus 1 is 8. Then you have error. Error is actually T into R minus 1. T into R minus 1, that is T into R minus 1 is, you can calculate, or otherwise total minus treatment, degrees of freedom. So 8 minus 2 is 6. If you put it in the formula also, you will get the same degrees of freedom. Right. What is the sum square that you have calculated? Sum square for treatment? 1 point something. Tell me the answer.
1.28.
28. Fine. What is the total sum square?
1.68.
68.
Now get the difference for error sum square. 0.
4.
Okay. Now what is the mean square? Mean square is sum square divided by degrees of freedom. So treatment sum square divided by treatment degrees of freedom. What is the value? 0. You divide by 2. 64. What about this? You have to use the calculator. Can someone tell me the answer? 0. 0.
99.
Okay, 99. Then what is the F value? 0.64 divided by 0.099. What is the value? F value? Anyone? We will have a huge value. Tell me. Any value? Yeah. Don't write it on chat, because I have to go and look at it one by one. Just tell me the answers.
6.46.
6.46?
6.4646.
No.
Yes.
Yes, sir.
6 point. So this
46.
is okay. 0.1, right? This is 0.1, right? Okay. 6.46. Right. So this is our calculated value. Now, how we can take the decision? How we can take the decision? Before we talk about decision, we'll have to put the null hypothesis. Null hypothesis in this example, alpha 1 is equal to alpha 2 is equal to alpha 3. Why only 3 alphas? Anyone? Why? Yeah. Why only 3 alphas? How many treatments are there? This is indicating first treatment difference. Yeah, second treatment effects, and this is third treatment effects. So alpha 1 is first treatment effect. Similarly, you can write down what is alpha 2 and alpha 3. First treatment effect, second treatment effect, and third treatment effect. Okay. All right. So alternative. alternative, at least, you can write down at least one alpha is not equal to 0. At least one alpha is not equal to 0. So that is your null and the alternative hypothesis. Somebody asked, is the mean square error is correct? I don't know. Mean square error, you all are the one giving me the answers. I said I don't have a calculator. You will have to use the calculator and tell me.
It will be 0.066.
Yes.
Yeah, somebody said 0.99, 0.099.
0.066.
66.
Which one is correct?
6.
0.066.
Yeah, so even using calculator, you all are doing mistake, huh? I don't have calculator, so that's why I said you do it. So this is 0.
6.
Which one? This one, huh?
Yes.
Yes, sir. Mean square of error.
Yeah, just a second. Zero point 066.
0.066.
Right. So what is change this value 0.066? What is the value there?
9.69.
9.69.
69.
Right. So this is our F calculated value. Actually, we need this for decision making process. Therefore, right now, right. So we will continue from here. So our null hypothesis, alternative hypothesis. Test statistics. From test statistics, we calculated the value. What is the value? 9 point. Calculated value.
9.6.
6. Okay, fine. Now we'll have to find out what is our table value, F table value. How to find out F table value? In your last course, we have seen the F table. Take out left F table. How many of you have F table? So we'll have to look at in two directions. This is numerator. Degrees of freedom. This is denominator. Degrees of freedom. This is numerator degrees of freedom. This is denominator degrees of freedom. Right? What is the numerator here? When you calculate this, right? F calculated. So here treatment mean square divided by error mean square. Or you can write it as mean square of error. So this is the numerator. This is the denominator. So what is the numerator degrees of freedom?
2.
2. What is the denominator degrees of freedom?
6.
6. So in the table, I don't have F table. You'll have to look at the F table. I think all of you have table. So in this direction, you'll have to look at for the value of 2. In this direction, we'll have to look at for the value of 6. Look at the values and tell me.
5.99. Sorry, 5.14.
Anybody having 5 point?
14.
Don't write it on chat because I cannot go back. We are wasting time. No enough facilities. So give me the values. don't write the values on the chat. If you have any problem, write on the chat, but don't write values on the chat. 5.14, right? Right. This is we have now our calculate value and table value. So, what is the table value?
5.14.
5.14. Suppose let's say this is our rejected region. So this margin is 5.14. We know our calculate value is 9.6. Right. Now this is non-rejecting region. I will put it as NR. This is a rejecting region. So this 9.6 falling into which region? Whether it is falling
Rejection.
into rejected region. Why? Because this 9.6 is falling somewhere there on a scale. So what is our conclusion? Since our calculate value is greater than table value, we reject our null hypothesis. We reject our null hypothesis. If you reject our null hypothesis, we can say, on the other hand, we can accept our alternative hypothesis. We can accept our alternative hypothesis. These are the decision-making process. Now we'll have to have conclusion. What is conclusion? Conclusion, we spoke about a few things. What is our experiment? You see, this is our experiment. What are these T1, T2, T3? What are these T1, T2, T3?
Different rations.
Different rations, right? Different rations for piggery. Right. Now, can somebody tell me, based on that different ration, how we can make the conclusion? Anyone? At least. I started, right. At least, tell me one ration. At least one ration is,
Not equal to.
we can't say ration is not equal to. What ration is doing? What did we measure?
Weight gain.
Huh? Weight
Weight
gain.
gain.
Now relate with ration.
At least one ration is causes for.
At least one ration. Oh, you can rename it rather than putting. At least one ration is resulting, rather than complicating. Yeah. Yeah. Anyone? At least one
ration is result in weight gain.
one ration, once again, is giving difference in
Weight gain.
average weight gain. Because we say average. Why? Because we average it for different replicates now. So at least one ration is giving difference in average weight gain. So this is more important. Now, because we said at least one ration is showing a difference in weight gain. So the next question comes, which ration? Somebody can ask which ration, isn't it? Because we said at least one of the ration is showing a difference in weight gain. One might can ask which ration is giving the difference in weight gain. To that answer, we'll look at it little later. Right? Weight gain, we'll look at it little later. By looking at just the data, we cannot come to a conclusion. So that, to answer that, which ration is giving more weight gain than which ration, we'll have to do a technique called as mean separation. Separation, SCPE. Mean separation. Right? We'll have to do a mean separation. Clear? So we do a mean separation. We will learn this mean separation. I will be teaching you mean separation, how to do it. That time we will look at it. Is it clear? Anyone need explanation? Is it okay? So that is the example we did for CRD, complete randomized design. Right. Now we will move to the other type of design. It is called as randomized block design. Randomized block design means all the treatments are going to appear in the block at least once, right? And also, meantime, when you talk about the term, new term, what is that? The block. What do you mean by block? We will see that also in this particular design. So, any experimental design in which the randomization of treatment is restricted to groups of experimental units within a predefined block or units assumed to be internally homogeneous is called as randomized block design. So we can take a small example on land, right? On land, we can take an example. Let's say I have 6 treatments. Each of these are experimental units. Randomly, I can allocate the treatment, not in order. You see, treatments are allocated for each of these experimental units on a random basis, right? So what we say is, if you look at this particular plot, or if look at this particular plot, or if you look at this particular plot, or if you look at this particular plot, all the plots are homogeneous. Give me some second. Huh? Okay, we'll continue. I said if you have a block, right? We will see what is the name of block. What do you mean by block and so on. So we have treatment, 6 treatment, right? Don't worry about how treatments have been allocated. 4, 5, 6, right? If you consider this experimental unit or this experimental unit, or if you consider this experimental unit, if you don't have any variation, or if you take this experimental unit A, B, and C, if all A, B, C are same in condition, if A, B, C all are in same condition, then we can say this is a homogeneous block. Can you all mute it? Homogeneous. Right? So if you have no difference between A, B, C as an example, then it is called as homogeneous units, experimental unit. So that is what we are expecting, internally homogeneous units. So that is called a block. So this is block 1. Block 2. Right? We have another set of block. Similarly, the third one, block 3. We have blocks. We have again 6 treatments allocated in each of these blocks, right? So, but what we expect here is, if you look at all the experimental unit are in the same condition, which is called as homogeneous, right? So that is what we are expecting. Right. What are the rules for blocking? What are the rules for blocking? First rule is, if you look at the rules, if you look at the rules very carefully, first information is you carefully examine the situation at hand and identify those factors which are known to be affected, so that we can have some kind of proposed blocking. So we'll have to examine. Normally, if you look at the land, if you do experiments in land, you should examine thoroughly before doing the experiment. All right. So choose one or two of these factors as the base for creating blocks. I will talk about what are the factors that we can consider for blocking purpose. Right? Suppose, let's say, if you have, I will say land, right? Let's say this is a river flowing water in this direction. A river is flowing water in this direction, right? Now we have a piece of land. I'm going to do an experiment in this piece of land. Very straight one. Huh? I have a piece of land. So in this land area, I'm going to do the experiment. Now tell me, I will mark some of the area like A, B, C, D. I said, what is this? What is happening? This is a river, as an example. This is a river, simply. This is a river. Oh, in Sinhala, it is called an ala or dola or whatever it is. In Tamil, ஒரு பக்கத்துல ஒரு சின்ன நீரூற்று, ஆறு அல்லது ஏதாவது ஒரு நீரூற்று, ஓடை, நீரோடை, தண்ணி போய் கொண்டிருக்கும். Right? Now tell me condition. I'm going to talk about condition here, A, condition here in B, condition in C, and condition D. Right? Clear? Right. Now, condition, if you look at different conditions in A, B, C, and D, can somebody comment about the condition? Which area is having more moisture? I said
A and C.
A and C.
A and C have more moisture, isn't it? Compared to B and C. Right. So that is very factor. I will say another one, E. I want to compare A, B, and E. Tell me which one is having higher moisture, which one is having second highest, and which one is having third highest. I'm comparing only these three.
A, E, B.
Right. A is having much
Higher.
higher moisture. Then E is
Then
having
E.
second, and B is. How do you call? Anyone from soil science? How do you call this kind of phenomena?
CP.
Yes, seepage. That is true, seepage. But we are not really talking about seepage. Can you remember Darcy's law? Have you learned soil physics? I can remember what I studied in 86, 87. Darcy's law. No? Yes?
Yes.
What does it say? I don't hear. What can you say about moisture here? Moisture gradient, isn't it? There's a moisture gradient. Can you all say there's a moisture gradient? In which direction? Opposite direction to the river flow, isn't it? There's a moisture gradient. So this phenomena is called as moisture gradient. This is called as moisture gradient. So there's a moisture gradient in this direction. So here the moisture is very high. Here the moisture is low compared. So this is called as, this phenomena is called as gradient. You can have any gradient. This is an example for moisture gradient. You can have a gradient for fertility of the land. All right. Similarly, another example. So this is, I'm going to have a plot in a slopey land. So there's a slope gradient, isn't it? So I can have the plot, right? In between these two, I can have the plot, but there's a gradient. This is called as slope gradient. So here it is a moisture gradient. Right. So here, now, can you remember in earlier definition, we want to create some homogeneous unit, homogeneous experimental unit. All right. So again, I'm drawing same river flowing in this direction. I have a piece of land where I'm going to do the experiment. Now I set here A, B, C, D. Now tell me in which direction I can make them plots which can be considered as homogeneous unit. For example, let's say if I go in this direction, it will bring homogeneous, or again assume this same block, huh? These two are same block, right? I can do it blocking in this way. This phenomena is called as blocking. This phenomena is called as blocking. Can you tell me whether this is correct or this is correct to bring homogeneous unit? So within the block, there is a homogeneous. Which way of blocking is correct? You can't say both.
First one.
Yeah. Somebody said this is, let's say, first way of blocking. This is second way of blocking, where you will create some homogeneous conditions within the block.
First one.
First one. How many says first one? How many says second one?
Second one.
First one.
Second one. Yeah, there are people second one. Why first one? What is the reason first one? Anyone? What is the reason for second one? Actually, you see the second one, first one, look at, see, because within the block, there should be homogeneous. Are we maintaining the homogeneous within the block? Yes or no? In the first one, are we maintaining the homogeneous within the block? So this is one block. This is second block. The third block, this one. And the fourth block, this one. So different colors. Are we maintaining the homogeneous in each blocks separately? Yes. What about this? So let's say here A, here B. Is this homogeneous, A and B, in terms of moisture level?
No.
No, different.
No, sir.
So that is wrong. So two blocking in second example or second way of blocking is wrong. All right. So suppose if the gradient in this example, the gradient is moisture. If the gradient is in this direction, all right. The water flow is in this direction. The moisture gradient is in this direction. This is moisture gradient. I'll put it as mg, moisture gradient. So how are we doing blocking? Parallel to the moisture gradient or perpendicular to the moisture gradient? So this making this kind of
Perpendicular.
yes, this kind of activity is called as blocking. So we are blocking. So this blocking is perpendicular or parallel to the gradient. Somebody said already it is perpendicular to the gradient. So don't forget, blocking is always done perpendicular to the gradient. Right, sorry. We'll go back. Go back to the lecture notes. Right, so now we will move to, right, I said blocking, right, I explained blocking, right. We'll come back with that example, right. This example I will talk about a little later. How blocks are formed is critical to the effectiveness of the analysis. Why we want to talk about blocking? What is the importance of blocking? With field blocks, blocks are laid out so that they are perpendicular to the maximum direction of change in the disturbing factor to be controlled. So disturbing factor, or we can call it as some kind of gradient. Either way is okay. Gradient, right? So that is basically we do the blocking. Once we do the blocking, by blocking we are expecting to have some kind of homogeneous conditions within the block, right? The second aspects of the importance of blocking, why border. Sometimes we may have to discard. The area are used to overcome interference between neighboring blocks and to maintain independence of response within blocks and between blocks. Sometimes that is also very important. When we expand the size of the block, let's say, suppose you are doing a small experiment. I think I don't know whether I mentioned last time. So here you have fertilizer experiment. 1, 2, 3, 4. Let's say a fertilizer experiment. Let's say F1, F2, F3, F4. The blocks are much closer. So what is the problem here? Can somebody tell me what is the problem if you do fertilizer experiment in adjoining blocks?
Border effect.
Yeah, border effect. Rather than saying what is happening, you are applying F1 fertilizer, some kind of mixture here. If you irrigate the field, there may be a chance where some of the nutrients, nutrients can move to the neighbor blocks through seepage of the water, right? So this danger is there. Similarly, the fertilizer can move to other blocks as well in this direction. So this is a big problem, right? So what we do is sometimes we may have to have larger plots, larger plot size. So here one plot fertilizer. Then we have small gully. Gully mean just no cultivation here. It's like a small ditch, no cultivation. Then we have F2, for example. Then we have another ditch. Then this is possible. Then F3. Then again ditch. Then F4. Suppose if you have so many treatment of this fertilizer, then you'll have to have very big block. Very big block. Big size of block. So we cannot get homogeneous. So then the plot of this, and if you take plot of this, is no more homogeneous. So that problem arises, right? So to avoid that, we can talk about the blocking concept. Right. Don't forget this important phrase. By blocking, we try to maximize the homogeneity within the block. We try to maximize the within block homogeneity. At the same time, we try to maximize the heterogeneity between the blocks or among the blocks, right? We try to maximize the heterogeneity among the block, right? Two different things. So if you have a block, for example, let's say I have two blocks, B1 and B2. So within the block, for example, this is what we said, within the block. Within the block, we maintain the homogeneity. Between the block, we maintain or we maximizing the heterogeneity, right? So let's say this is the direction of gradient. This is the direction of gradient. Whatever the gradient, maybe moisture or fertility or whatever it is. So don't forget this phrase. So within the block, we try to maximize the homogeneity. Between the block, we try to maximize the heterogeneity. Two different things. Right. Now example, blocking. Moisture gradient. If you have moisture gradient, can somebody tell me whether blocking, this is a one block, right? This is a single block, right? This is a single block. There is block 1, this is block 2, block 3, and so on. Now, can you tell me whether this way of blocking is correct or wrong? Tell me whether these units are homogeneous units in terms of moisture.
No.
Huh? No. For example, there's a moisture gradient. So, right, this way of blocking is not a good thing. Why? Statistically, we say that treatment effects are confounded. Treatment effects are confounded with moisture effect. So that is the problem. Treatment effects are confounded with moisture effect. Right? We cannot separate the moisture effect and the treatment effect. So that is called as basically confounded. Right? Then we look at the second example. If the moisture gradient is that direction, how about this one?
Correct.
Correct. So this way of blocking is correct. Why? Because this is one block. block 1, let's say B1, this is B2, and so on, B3. Look at this example, B1, treatment 1, and treatment 2, which is on the other corner. There's a homogeneity here. If you look at the moisture level at this plot, and this plot is more or less same. Why? The gradient is in this direction. Okay? Clear? Right. 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 This way of blocking is correct. What about this environmental gradient in this direction? Right? Environmental gradient, whatever the gradient, maybe temperature or light or whatever it is. Then blocking is perpendicular to the gradient. Who is, can you mute it? Right. So this is correct way of doing blocking. For example, within the block, how many treatments are there? You see, within the block, 3 treatments. They are also randomly allocated. You see, here treatment black color, green color, and the white color. So randomly allocated. Right. Now let's look at because we already said you are always in doing the blocking perpendicular to the gradient. Now let's look at some of the examples on blocking, factors that we can consider during blocking. Nutrient gradient in the field plot. When you do experiments in the field plot, there may be a gradient, nutrient gradient, moisture gradient, right? Water or moisture gradient, slope differences, right? Slope may be different, soil composite may be different. So in those cases, we can do the blocking separately, right? Perpendicular to the gradient. Then another example, orientation to the sun. Especially, even though we said greenhouses, you rarely find a problem. Greenhouses more or less homogeneous. But there may be opportunity to have heterogeneous also, right? Why? Because if the greenhouse located in a place where sometimes you may get light, sunlight, which is coming into the greenhouse. Maybe flow of air, if you have some exhaust fans or some heat or air condition, for example, sitting closer to the air condition is much colder, isn't it, than sitting little away from air condition. So distribution of heat, all these are matter we can have blocking. Then in animals or trees, age difference are there, so you can block it, right? Maybe weight difference are there, we can do the blocking. Among the people, gender, we can do the blocking. Age, again, we can do the blocking. Sometimes socio-demographics, let's say the income level of farmers. If you can group it to different income levels of farmers, we can do the block. Right? So those are some concept of blocking. Right. Advantage and disadvantage of blocking. There are advantage, control the single extraneous source of variation and remove its effect from estimate of experimental error. allows more flexibility in experimental layout, allows more flexibility in experimental implementation and administration. Disadvantage of block design, generally not suit for especially if you have large number of treatments, the block will be very big. Block size will be very big. Within the block, we cannot maintain the homogeneity. So what do you mean by that? Let's say I have 20 treatment. I have 20 treatment, right? So I have 20 treatment. I'm dividing this into 20 blocks. Sorry, 20 plots. 20 plots. So if you look at the homogeneity of these two plots, they don't perform with the homogeneity, right? Generally unsuit when there is a large number of treatments because of possible loss of within block homogeneity. Serious problem with the analysis if a block factor by treatment interaction effects. So that is you will learn later on. Mainly this block and treatment interaction. We call it as interaction effect. Block factor with treatment interaction. Block factor with treatment interaction is basically may exist if you don't have a replication within the block, which has been a problem in the analysis, right? Right. Complete or incomplete design. Complete means, let's say I have 4 treatment. Sorry. I have 4 treatment, A, B, C, D. 4 treatment. You see, this is one block. This is one block. This is second block. This third block. Right. So all 4 treatments are present in this. So it is called as complete. Here, look at one block. How many treatments are there? Only 3. A, B, C. Here D is missing. Here C is missing. Here B is missing, as an example. So this is called as incompleteness. Out of 4 treatment, only 3 is appearing in each block. So this is called as incomplete block design. Complete means all the treatments are appearing in a single block. Okay. Balanced design, I said if the number of replications are equal, it is called as balanced design. So balanced block design means if the variance of difference between 2 treatment means is the same regardless of which 2 treatments are compared, then this is usually implies that the overall replications for the comparison of 2 treatment is the same for all pairs of treatments. Partially balanced, right? Partially balanced, you will not learn in this particular course. Balanced block design, right? For example, even though this is an incomplete, look at this example. A, how many times A replicated in this example? Incomplete. Even though it is incomplete, how many times A replicated? B,
3 times.
C, and D. Huh?
3 times.
A 3 times, B
2 times.
B 2 times.
C 2 times. D 3 times.
D 3 times. Are you sure?
D 2 times.
2 times.
Hmm?
D2.
D2. What about C? 2 times. B? 2
2.
times. A 3 times.
A3.
So this is called as, you see how many replicates are there? I mean, how many groups of replication? One group is having 3 replicate, the other group is having 2 replicates. So this is called as partially balanced. Partially balanced. If you want to have even in incomplete, you can have balance. Can you tell me how we can put into balance? Anyone? Look at this example. I will. Just a second. Now tell me how many times A appearing?
Equal. All are 3.
Yeah, number. Yeah,
3.
A 3 times, B.
D 3 times. C was 3. D 3.
Now you see, this is called as balanced. Right? So the early example, partially balanced. 2 groups are there. One group is with 3 replicate, the other group is with 2 replicate. So if all are having same number of replicates, then it is balanced, right? So that is called as balanced design. Okay. So in this case, we have balanced as well as partially balanced situation. Unbalanced. So unequal, partially balanced, I mean unequal replication in each block. Sometimes some treatment having 3 replicates, some having 2, some having 5, and so on. Right? Right. We will talk about the model in the next class. We will stop with that. Right? Any questions? The next class we will be probably facing 1-to-1, right? I'm not sure. Maybe third. Third, we might meet for the first time in the class for this particular course. Yeah. Anyone would like to ask any questions? Right. If not,